How's it going, Calc kids? Today we're looking at 4.3, connecting the graph of f prime, f double prime with the graph of your original function. We're going to learn the first derivative test, concavity, points of inflection, second derivative test, and we're going to have fun learning about functions and derivatives. Okay. First things first. The first derivative test for local extrema. If you guys want, I can get you this picture, or you can just look in your book. It's there. I really like this picture, though. When you look at it, you can see wherever f prime equals 0 or is undefined, you're going to have a max or min plus endpoints. Okay? Local or absolute. Actually, this one, there is no extreme, and this one as well. Those are a point of inflection. Okay? And you can also see here, your derivatives positive, derivatives negative, derivatives positive, derivatives negative, negative. So decreasing, decreasing, increasing, decreasing, increasing, increasing. Okay, so those of you who may have been struggling on this thus far with the graphs, this graph's a great thing to look at and really think about. Okay, have a deep thought about how you feel about it. It's too far. Far too far. Okay. See this junk? It's important. You're going to have to take some time and write this. Use it. Love it. Just fall in love with this all over again. Wherever your derivative equals 0 is a critical point. I do believe we've talked about that before. If your derivative goes from positive to negative at c, you have a max. So if you go from positive to negative, you have a max. Because you went from an increasing slope to a decreasing slope. So it creates one of those bumps, you got a max. Okay. If it does not change, if it goes from negative to positive, then it's a min, because it's going to go negative to positive. And here was your critical point. If it does not change value, so like from a positive to a positive, it's nothing. Or from a negative to a negative. Okay? And the other thing you have to do is plug in your endpoints to see if those are bigger or smaller than your other points, because then they might be local maxes or local mins. Okay? Okay. Okay. Here we go. Let's take a look. Use the first derivative test to find local extreme values. Identify any extreme. We're getting to this point in our curriculum where we're figuring out, in calc, you pretty much take the first derivative for everything. So let's start there and take our first derivative. Okay, so f prime of x, and we know this one now pretty easily. It's 3x squared minus 27, and the 3 goes away. Okay? Now we have to find critical points. Okay? Critical points. To do that, you take your derivative and you set it equal to 0. Okay? And then you solve. So we're going to add 27. 3x squared equals 27. X squared divided by 3 is 9. So we have 2, right? So when you square root both sides, you get x equals 3 and negative 3. So those are our critical points. Critical points. Okay? So, here's what we need to do. Do you guys remember these T-chart things we used to have back in the day? -3 and 3 are critical points, right? And here we're going to analyze our derivative, our first derivative, f prime of x. Okay? So we're going to plug in points and see where it's positive and negative. So let's take the point 0. I'm just grabbing points, okay? I use 0 because it's easy to do. And I plug it into, my derivative. And I get a negative answer, okay? So now let's plug in a number that's bigger than 3. Let's plug in 100,000 million. Okay, and when I plug that into my derivative function, well, that's going to be positive. Because 100 million squared is like 100 million, so it's going to be positive. Okay? So now let's plug in our point over here. Let's plug in our negative 1,000 bazillion million and plug it into our derivative. And we get a positive. Because anything negative squared is positive. So it's positive. So that means at negative 3, okay, we're going to have a local max. Because we went from positive to negative. So you go up, and then you start to come down. Okay, so it's going to be a bump. Okay? So at negative 3, we have a local max. Now we want to know what that local max is. So we take our negative 3 and we plug it into our original equation. Okay? When you plug that in, you get 57. So 57 is the max and it occurs at negative 3. Okay? So again, 57, this is the max, local, and it occurs at negative 3. Okay? So that means positive 3 is going to be a min, a local min. Okay? And we plug in 3 into our derivative, not our derivative, our original equation. Original equation, that should have been negative up here. And when you plug that in, you get negative 51. So that's your local min. And it occurs at 3. Okay? Now, these are local and not absolute, because if you look at your original equation, it's going to look something like this, right? Because it looks something like this, it goes to infinity and negative infinity. Hence, you don't have an absolute maximum. Okay? Okay, I'm going to pause for time. Time looks pretty good. Okay, let's talk about concavity. And not the ones in your mouth. Cavity, never mind. Okay. Okay. Concave up says that your derivative is constantly increasing. Okay? Hence your second derivative will be positive. So concave up means that it's a nice cave that a bear can live in. Okay? Concave up, the bear is happy. Okay? Concave down, the bear is depressed because it's going to slide down the hill and fall into its a doom. Fire, I guess. Anyway, concave up, the bear can stay there. He's happy. His moves up, down, he's depressed because he's going to slide down. Okay? So again, this would be up, this would be down. Okay, where's the bear going to live here? Here, a bear is happy as can be. Yay, bear. Here, the bear falls off the cliff. Okay? Concave down, your derivative is constantly decreasing, up, increasing. Okay? Okay. Here's your concavity test. Okay? You are concave up where your second derivative is greater than 0. You're concave down where your second derivative is less than 0. Okay? So this is the same test you used for increasing that we did last section, but now we're looking at concavity. Okay? This is important because if you have concavity up, that means your investment is good because it'll keep going up higher and higher and higher. Okay? Okay. Write that down. So now let's take a look at this function f of x equals x squared and use our concavity test to see if it is up or down from 2 to 8. Okay. Our first derivative is 2x, right? So now we take the second derivative, f double prime, is 2. So is there ever going to be a time where this is negative? No. So this is always concave up. Which makes sense because the function looks like this. Okay? And a bear can live in there. Okay? Okay. Now, a point where the concavity changes from up to down is called a point of inflection. Okay, and usually they look like this. This point right here would be your point where you go from concave down to concave up. Okay, point of inflection. It's where you sit and you think about yourself and the choices you've made and whether or not they were good. You inflect. Okay. Also, this is going to be where your second derivative equals 0 and the concavity changes. Okay? Okay. One more example, I do believe. Is there? No. Lots more. Okay, so let's find some points of inflection. This is a function. Okay? So the first thing I need to do is find y prime. Well, the derivative of e to anything is still e to whatever that dealio is. And we times it by the derivative of the function side function. Good old chain rule, right? So the derivative of that there is negative 2x. Okay? So we end up with negative 4x e to the x squared. There's a negative right there. Okay? Y double prime. Oh man. Now we have to use our product rule because we have a function times a function. Okay. So y double prime. My u is negative 4x. So my u prime is negative 4. My v is e to the negative x squared. My v prime, guess what? We already did this once before, and it's this function, right? Because we're taking the derivative of this, but without a u. So it's actually going to be negative 2x e to the negative x squared. If you didn't see how I did that, just ask me in class and I'll talk about it. Okay, so then we do our cross multiplication. We get negative 4 e to the negative x squared plus negative 8. Well, it'd be a positive because we're multiplying x squared e to the negative x squared. I just multiplied my u and my v prime. Okay? So, now what I'm going to do is I'm going to, this is my y double prime. Okay? And I'm going to try to find out my points of inflection. So I'm going to take this and I'm going to set it equal to 0. Okay? Now what I'm going to do next will amaze you. All these have a 4 in common, right? So I can pull a 4 out in front. they also have an e to the negative x squared. So I'm going to pull that out in front. Okay. Times, well, this becomes negative 1, right? Because that negative will still be left there. Plus 2, 8 divided by 4 is 2, x squared. We set that equal to 0. Okay? So, now what we do is we divide both sides by 4e to the negative x squared. That's 0, that's 0. So we get 2x squared minus 1 equals 0. Phew. Add 1, add 1. 2x squared equals 1. X squared equals 1/2. And x equals plus or minus the square root of 1 over 2. See square root both sides. We have 2 points of inflection. Square root of 1/2. Negative square root of 1/2. That was a long problem. I gotta check for time. I got one more arrow to put in your guys' quiver. The second derivative test for local extrema. Okay. If you find your critical points where your derivative is 0 and your second derivative is 0, or no, your first derivative is 0. If you take the second derivative, okay, and it's negative, then it has a local max. So if f double prime of x is negative and f prime of x is 0, then you have a max. Okay? Now if f prime of x is 0 and f double prime of x is positive, you have a min. Okay? So, one more example. Okay. Find the local extreme values of this function. Here's our first derivative, and here's our second derivative. Okay? So the first thing I'm going to do, well, you guys need to write this down first. I know, it's such a long video. First thing I need to do is take this and set it equal to 0. Okay? So when I do this, I get Moby. No. When I do this, I get 3x squared equals 6. Okay, 3x squared equals 6. X, I can't do it. Let's see if it'll work. Just finish this problem. X squared equals 2. So x equals positive root 2 and negative root 2, right? Square root both sides. So those are my two zeros. So now to find out if they're a max or a min, I plug them into my second derivative. So this equals 6 square root of 2 for my second derivative. So since that is a positive number, this will be a local max. Now if I take my second derivative and I plug in my negative root 2, I get negative 6 root 2. Since this is negative, it's a local min. Okay, so if your second derivative is positive, max, second derivative is negative, min. That's it. Enjoy.